Look at this nighttime view of a modern metropolitan region. You are looking at a living, emergent system, a dense web of economic exchanges, traffic flows, and shifting populations that constantly adapts to new data. Yet, if you walk into a traditional urban planning classroom, you'll often find this complex reality flattened into a static spatial puzzle. The city is treated as a clean grid, with a predefined problem waiting for an architectural solution. We are educating professionals who will step out into highly unpredictable, chaotic urban ecosystems, but we are training them using neat, pre-packaged design assignments. These traditional studios heavily reward spatial imagination and the ability to draw a compelling master plan. They do not demand the evidence-based reasoning required to analyze large-scale mobility datasets or track real-time urban sensing. Teaching a student how to execute a pristine design brief guarantees they can draw a plan. It leaves them completely unequipped to discover and diagnose actual urban problems when the variables are hidden. Over the last 30 years, two distinct active learning methods have dominated this space: project-based learning and problem-based learning. Project-based learning operates on a simple driving question: what should we produce? The goal is always a tangible deliverable, a final plan, a rendering, or a physical model. Problem-based learning asks an entirely different question: what is actually happening here, and why? The focus shifts away from making an object and toward investigating an ambiguous situation. Project-based learning is highly effective for building specific professional skills. It forces students to collaborate, manage time against a strict deadline, and present to a client. Problem-based learning is built to train scientific habits of mind. Students must confront incomplete data, integrate different disciplines, and build their own theoretical models to make sense of a chaotic environment. Choosing between these two methods requires accepting a strict trade-off. You are prioritizing either the predictable production of a polished artifact or the rigorous, messy construction of deep understanding. In a standard project-based studio, day one is highly structured. The instructor hands the students a specific site, a detailed design brief, and a fixed timeline. This diagram shows the divergent logic at play here. You start with one clear prompt, which diverges outward as different student groups apply their skills to produce several unique final artifacts. The immediate benefit is clarity. Because the constraints are locked in, students can dedicate all their energy to synthesis, spatial design, and mastering their rendering software. But there is a hidden cost. Because the problem was handed to them on a syllabus, these students never practice the act of looking at an ambiguous real-world situation and isolating the actual problem themselves. In modern urban informatics, extracting a clear problem from massive datasets is the hardest part of the job. Knowing how to render a beautiful solution is useless if you are solving the wrong problem. Problem-based learning starts with an ill-structured phenomenon, like the informal vendor economy in this street market. Students arrive with no brief, no assigned variables, and no clear instructions on what to design. This flowchart illustrates the convergent logic of the method. To make sense of the market, students have to pull independent strands, like GIS data, urban theory, and field observation, and converge them into a single, unified insight. Early on, this approach generates intense anxiety in the classroom. Students are used to being graded on deliverables, and right now, there is nothing tangible for them to build. This friction is intentional. The learning resides in the iterative process of wrestling with the data, rather than the polished quality of any final output. To prevent that anxiety, problem-based learning uses a strict 5-step framework.
The cycle begins with step 1, describe. Students conduct rigorous audits of observable phenomena. They map pedestrian flow, document land use, and log vegetation, all without making a single judgment or proposing any solutions. Before massive computational datasets existed, early urbanists like Jane Jacobs relied entirely on this intense, boots-on-the-ground empirical observation to map how human networks actually functioned. The trade-off here is patience. Action-oriented students will want to start designing immediately, and this step forces them to delay that gratification. Once observations are logged, the cycle moves to step 2, inquire. Students transition from describing what is there to formulating hypotheses about why it's there. For instructors, the workload shifts heavily. They must facilitate real-time access to data and experts to support student questions. By locking students into these first 2 steps, we prevent them from jumping to architectural conclusions. They are forced to anchor their thinking in empirical reality. Now the technical work begins at step 3, model. Students build computational models to test their generated hypotheses. This is a massive technical hurdle where models frequently break. Students must learn to treat a broken model as useful data rather than a failing grade. At step 4, extract, students parse models to identify scaling relationships, detect temporal dynamics, and pinpoint spatial inequities. Instructors must adapt here too, using rubrics designed to measure analytical reasoning and sensitivity to data anomalies. Visual polish becomes a secondary metric. Finally, the cycle arrives at step 5, state. Only now do students articulate spatial strategies and design guidelines, which must directly respond to the extracted data. The visual deliverables might look underwhelming compared to glossy master plans, but their spatial logic is deeply epistemically rigorous. Mastering this loop of observation, modeling, and extraction is the exact mechanism that upgrades a student from a spatial designer into an evidence-based urban scientist. Transitioning to this framework carries a high organizational cost. For many academic staff, moving away from project-based learning means dismantling their own professional identity. In traditional studios, instructors operate comfortably as expert design critics. They assign the work, review the completed artifacts, and dispense aesthetic judgments. Problem-based learning strips away that authority. Instructors must step down as the ultimate judge of an artifact and become Socratic facilitators of uncertainty. Practically, this means knowing when a student's model is poorly calibrated, but resisting the urge to fix it for them. You use your expertise to ask a harder question, forcing the student to resolve the contradiction themselves. PBL places a heavy burden on both sides of the lectern. It forces entire departments to rewire their rubrics, their studio culture, and the very way they measure intellectual success. So for department heads planning a curriculum, the question is, do you abandon project-based learning entirely? The answer is no. This matrix maps out a degree program. On the bottom, we move from foundational semesters to the final capstone. On the vertical axis, we move from analytical rigor up to production output. The 5-step problem-based framework belongs firmly in the early and middle semesters. This is where you build scientific formation, inquiry, and system-level thinking. Project-based learning is reserved strictly for late-stage professional practice units and final capstones, where students must synthesize their knowledge and present a polished deliverable to a client. You do not have to choose just one methodology, but you must sequence them correctly. Use problem-based learning first to teach students how to think about complexity. Use project-based learning later to teach them how to produce the final result.